Okay, great. So my name is Volodymyr, and I'm a PhD student in University of Bayreuth, working on the wedge between chemistry and material science. And today I will talk about how I use the ORKG for material science research and making some comparisons. So let's talk first why material science is important, and especially in the field of plastics. So everyone knows that plastic is currently a very huge problem, and almost 40% of all plastic is used for packaging. So we produce so many packaging as per year. In Germany, we produce almost 38 kilos of plastic per person, and 32% of this plastic is disposed improperly. That means it end up in nature. So, for example, currently there is almost 6 times more plastic in tons than plankton in oceans, and only 1% of this plastic is biodegradable. So, and if we want to replace the whole of this plastic by biodegradable polymer, we want to do something better because biodegradable polymers are very bad in barrier properties. That means they don't really protect our food from oxygen and from water, so it spoils fast. So depending on the type of product with which you want to pack, you have a very different barrier requirements. So on the graph to the left, you can see the oxygen transmission rate and water transmission rate for different products. So for example, for fruits and vegetables, we don't really care about the barrier properties. But for example, if you want to have crispy chips or pretzels, or for example, your instant coffee to be fresh, you need to have a pretty severe requirements for barrier properties. And commonly used plastics allows you to preserve food only for 12 and up to 40 days, and we want to make it longer. So one of the solutions is to make a nanocomposites. So in this case of nanocomposites, you have a polymer and a filler, usually a plate-like filler with a different aspect ratio, where aspect ratio is the ratio between length and the thickness of the filler. So if we add just some kind of filler to our polymer, we can improve the barrier properties, and depending on the size of this filler, we can improve it from 100 to millions. So, and that's where I come to my research topic, which is synthetic hectorides. So this is synthetic clays which produce on our faculty, and the key feature of this clay is that it has a very huge aspect ratio. So that means the thickness of the single nanosheet is only 1 nanometer, and the diameter is 20 micrometers. Uh, and uh, and when you put it into water, it swells osmotically to very high uh, distances, and it can be used to make nanocomposites. And this is exactly what one of my comparisons is. So we look on how the synthetic hectorides can improve the barrier properties. So in this case, when we're talking about these materials, we're interested on from which polymer we use, how much of the filler we use, and what's how we prepare them, and also what kind of properties we actually achieve. So in terms of how they're produced, so the ORKG offers a very nice way of using templates, and also Wikidata, where you can link directly, for example, your polymer material to the Wikidata, so that people can easily read about this polymer or cross-check how this polymer is used in other fields. And second, also a great feature of ORKG is that you can input your measurement values together with the measurement conditions, because in case of the barrier coatings, this is incredibly important. And if we take an example of one of the coatings where we do the measurements with this conditions of relative humidity of 65, we have barrier coating barrier values of 0.002, which is very, very good barrier. But if we go to higher relative humidities, to the 90 relative humidity, we have a barrier of only 0.34. What it means? That means that in the first case, we can use easily this coating to pack the instant coffee. But if we have an atmosphere of higher relative humidity, saying that we're in the Asia region, then suddenly we cannot use it anymore. So, and another important part of my research is that this barrier coatings is not only good for barrier, but also for mechanical properties, because they are have so they have represent the structure of the natural nacre, which is consists of the very small amount of organic phase and inorganic phase, which in the nacre is an aragonite crystals. So what's unique about this material is that it's simultaneously strong and tough, which is an unusual combination for the nature. So in this case, I took also another comparisons where I studied the mechanical properties of nacres based on reduced graphene oxide, which is readily available and very popular material right now. And what we get is when we are looking on the nacre, we're interested in from which material we fabricate it, how we fabricate it, and what strength, toughness, and Young modules we achieve. So the strength means at which point material will break. Toughness means how much of energy it can absorb and dissipate. And Young module says how difficult it is to deform material. So saying that we have a rubber, it has a very high toughness, it has a high strength, but it has a very low Young module. So that means it's very easy to deform it. But if we take a ceramic, it has a very high strength and very high Young modules, but very weak toughness. That means it breaks easily without the deformation and it's not really absorbing energy. And oh yeah, so what's another feature of ORKG which I would like to show is that, sorry, I will share now screen differently. So another feature is visualization. So here in this example, we're comparing the Young modules and strength of material, and we can see that these two properties are actually decoupled, where we can have simultaneously a very high strength. So for example, in the case of RTO PS PB, but very low Young modules. And the last point which I wanted to share is the knowledge graph. And it's one of the another interesting aspects of ORKG, where you can have an information about your material, including its properties and also its values and units. And what's another point which I wanted to highlight is that at the beginning of ORKG, I encountered certain problems with the terminologies. So it could be a little bit hard when people use Young modules, Young's modules, and so on and so forth, where they mean the same thing, but the computer see it differently. So the nice feature of being able to add tags to the properties, so saying that we tag a Young module same as Young modules, and we can compare the data from the different sources where a computer can understand that it's really the same parameter, but for people it's easier to kind of get used to what they're really using in the everyday token. So that's it. I wanted to say thank you for ORKG team. So as soon as my research topic is not really connected to the knowledge and semantics, it was at the beginning pretty hard to understand these relationships, but it was a great experience, and thank you very much.